Boldly going where no science show has gone before. The Naked Scientists.
Well, this week, what do TB and Goldilocks have in common? Well, scientists have found that some people have a gene combination that is just right for the bug to flourish in them, and we'll find out what it is and how it might help to tackle the disease in future. Also, why a new discovery lurking off the coast of Siberia could spell disaster for the Earth's climate. Sounds spooky, we'll hear more in a second. And also knocking migraines on the head with magnetism. We'll be hearing how doctors have found that a burst from a magnet can stop a migraine in its tracks, which is eminently more attractive than actually having the headache. Hello, welcome to this week's Naked Scientists. I'm Chris Smith, and also here to help present the programme this week is Diana O'Carroll.
Yes, it's me, and also this week we're looking at the science of solar energy. We'll be hearing how scientists are developing new materials to maximise power production, how architects are drawing up better buildings to minimise electricity bills and make the most of the free energy from the sun, and a new flexible solar material that can be rolled up and even turned into a tent.
Perfect for my camping holidays. Not sure if it works in Scotland though. We'll find out. Thank you very much, Diana. Now, also on the subject of solar cells, in this week's Kitchen Science, Ben and Dave will show you how you can make one of your very own. That's coming up. So if you have any questions or you just want to say hi, have some feedback for us, do get in touch. The email address is chris@thenakedscientist.com, or you can send us a tweet. It's @NakedScientists.
The Naked Scientists Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
This is The Naked Scientists with me, Chris Smith.
And me, Diana O'Carroll. And this week in the news, it looks like researchers have discovered a key reason why some people are susceptible to TB, tuberculosis, and others aren't. Publishing in the journal Cell, Lalita Ramakrishnan and colleagues from the University of Washington think that it's the levels of an enzyme called LTA4H, which gives some people better immunity. And it's not those with more of the enzyme who are the winners, nor the people with the lowest levels of LTA4H. Similar to Goldilocks and the Three Bears, it's actually those individuals who have a middling or just right amount of the immune enzyme who have TB resistance. Now, people who are heterozygous or have two different versions of the gene which makes LTA4H have this middling amount of the enzyme, and the researchers tested this in a controlled environment by looking at zebrafish, which had been selected to produce different levels of the enzyme, and it became apparent that LTA4H was playing the same role in their immunity. Now, Ramakrishnan then compared her findings with human geneticists from Washington and Vietnam and Nepal to see if they were the same, and it emerged that it was this heterozygosity in people which produced the ideal levels of the enzyme. What's interesting about this is that for a long time it's been known that people with a nasty case of TB may improve if you give them a dose of anti-inflammatories. It may be that these people are producing too much of LTA4H, and by giving them anti-inflammatories you reduce the effect of the enzyme to a medium level, and this makes life difficult for the TB bacteria, making the patient feel better. And it's an important finding because there are now so many new strains of TB which are drug resistant. So if you can tinker with the human immune system instead, then you might come up with a better solution to the problem. Plus there's the added bonus that LTA4H also confers immunity to other mycobacterial infections like leprosy.
And of course, with so many people infected, something like 1 person in 3 worldwide, and spreading at huge numbers, and I think it's 10,000 new infections, 10,000 deaths a day, TB is probably one of the worst scourges that exists in the world at the moment, I would say.
Yeah, and it's affected quite a few people in the UK recently as well. It's not exactly a dead disease here.
No, something like 10,000 new cases a year in the UK. I think it's up from almost got rid of, and people were very enthusiastic in the sort of antibiotic era, and it has made a resurgence because it's become resistant, so new ways to tackle it, very important.
Indeed.
Now, from one very new discovery to another very new and very worrying discovery indeed, scientists have found that there are millions of tonnes of sequestered methane which are locked up underneath the shallow ocean shoreline of the Arctic coast of Siberia. And these methane deposits are becoming unstable and they're escaping into the air, actually in the form of millions of tonnes of it coming out every year. Just from a 2 million square mile area, there are more tonnage of methane coming out than there are actually methane coming out of all of the rest of the world's oceans. So this could have a catastrophic effect on climate change in the future, especially if the amount coming out increases. This is a piece of research that's been done by someone called Natalia Shikova. She's a researcher at the University of Alaska at Fairbanks. And what she and her team did was, over a number of years, go to this bit of Siberia and take measurements from both the water and the air above the water to measure how much methane is in there. And what they've discovered is that the water is saturated with methane. Now, the interesting thing about this bit of coastline is it's very shallow. The water there is less than 50 metres deep, and it's only been flooded for between 5,000 and 7,000 years, a maximum of 15,000 years. And what the researchers think is going on is that there are forms of methane there called methane clathrates. And this is when you put water under a certain temperature and a certain pressure, you get the water molecules forming little watery cages with a hole in the middle, which can soak up some gas, in this case a methane molecule. Now, if you destabilise those clathrates, the methane can come out, and this means it will bubble up to the surface. And their concern is that there's so much methane coming out, they think that the warm water of the oceans flooding into this area in the last 5,000 to 10,000 years, plus global warming on top of this, may be destabilising these deposits, and the whole ocean area could just burp up a huge amount of this methane, and this could have enormous consequences for climate change, because methane is between 30 and 50 times more potent as a greenhouse gas than CO2. So if the methane comes out, it will obviously make the world warmer, and that will accelerate the problem that made it come out in the first place. So it could make a sort of positive feedback loop or a vicious cycle. So let's hope not, but it's certainly important to keep on monitoring this now they've discovered it. Diana.
Pretty frightening stuff. Well, also this week, on a slightly lighter side, archaeologists have described the discovery of some of the earliest evidence for advanced human thought. Now, publishing in the journal PNAS, Pierre-Jean Texier and colleagues have analysed nearly 300 bits of carved ostrich shell from a site in South Africa. Now, these shell fragments are thought to be about 65,000 years old and were found at the site of Diepkloof rock shelter, where there are layers and layers of Middle Stone Age archaeology. These eggshell fragments have a fairly common motif on them, which involves the scoring of two parallel lines and some cross-hatching, which links them, so they actually look a bit like a simplified picket fence drawing. It doesn't sound like a very hard graphic to achieve, so it could just be someone doodling, perhaps. The authors of the study think not, because the design was prevalent on so many pieces, and also when they tried to copy the design using knapped flints and a new ostrich egg, they found it was really tough to actually score any sorts of lines on the surface.
So someone was making a determined effort.
Exactly. They're actually working quite hard at doing this, and they were doing it repetitively as well. So it does seem intentional. And it's not the first evidence of artwork per se, as there have been shell bead discoveries, also from Africa, about 75,000 years old, and there are some more examples further away, this time in Israel, which date back about 90,000 years. But these ostrich shells are one of the earliest examples of graphic design. It's important because it demonstrates what's known as symbolic thought, the idea that some kind of decoration or image can carry a meaning that's understood by other members of your society. So, for example, if you have a decoration on your ostrich egg water vessel it might have been used for, it might imply that you belong to a particular group of people. Maybe you're making yourself more attractive by doing it, or maybe it was something only the adults or the women did. We may never know what these graphics mean, but they do point to some sort of advance in human thought about 65,000 years ago.
And to put that into context, of course, the first writing appeared only in the last, 5,000, 4,000 BC?
About that. Actually, I think there's some evidence about 6,000 BC.
But this means this is very, very, very early, 10 times older than that. People were putting something which is akin to writing, I suppose. It's symbols onto an object, which argues for a very big thought process jump, doesn't it? A long time ago.
Yeah, and it's actually about 20,000 years earlier than the previously imagined great cognitive leap that, people were saying when humans moved into the European continent. Suddenly they had this fantastic cognitive leap. But no, actually this is happening 25,000 years earlier in Africa.
Tremendous. We'll also talk about Africa. There's a researcher at the University of Rochester, John Tarduno, who's published a paper in the journal Science this week. And what he and his colleagues have done is to wind back the first or earliest evidence for the Earth's magnetic field existing by a good 250 million years. So scientists don't exactly know when the Earth first came by its magnetic field. Sometime at the moment around about 3.2 billion years ago. We know there's evidence for the magnetic field being there. This is the evidence that it's there from 3.5 billion years ago. What they did was to scour South Africa for some very old rock samples, some quartz, and what they then did was to put those grains of quartz into a very sensitive magnetic device called a SQUID, which is a superconducting quantum interference device. That's why they call it a SQUID. And this is capable of measuring very, very sensitive changes in magnetic fields. And when a rock is forming, when it's molten, any particles that are magnetically active in the rock, when they can move around in the molten rock, will line themselves up with the Earth's magnetic field if it exists at the time. And then when the rock cools, they're locked into position. So if you put those rock samples into one of these devices that can read these magnetic signals, and you then heat the rock up, as its magnetic fingerprint, if you like, flicks back into line with the magnetic field in the device, you can register how much it's changed and therefore what was written into it in the first place. And that's how we can work out that these rock samples that were 3.5 billion years old had a signature of the early Earth's magnetic field written into them. The interesting thing, though, it was only about 50 to 70% as strong as it is now. The consequences of that would be that the northern and southern lights, the aurora that we see, would have been a lot bigger and a lot more intense. Some people are saying they would have been visible even as far south as where London and New York are now, and that would have probably been the same in the southern hemisphere. But the other point is that the Earth would have taken much more of a battering from the solar wind, because although the sun was younger then, it was ejecting enormous amounts of charged particles in this solar wind, and so the Earth probably had a lot of its lighter molecules and a lot of its water stripped away by this intense battering, coupled with a reduction in the magnetic field. But the really interesting thing is that we know life got started on Earth also around the same time as these researchers have found this magnetic field being in existence, and we know the magnetic field is critical to protect the Earth from being totally basted by solar radiation, and therefore this kind of fits with when we saw life appear, and therefore this is the first evidence for the Earth's magnetic field, probably the key thing that we had that catalysed the existence of life on Earth to start with.
Brilliant. So they had something, they didn't have any factor 50 then, which is what I have to use.
No, they didn't. But indeed, you didn't have that to rely on, but you did have a magnetic field. OK, well, also in the news this week, researchers have shown that you can knock migraines on the head, talking magnetism, with a magnet. And Dr. Richard Lipton is a neurologist at the Albert Einstein College of Medicine. What a great place to work. He's based in New York and he's with us now. Hello, Richard.
Hi there.
Welcome to The Naked Scientist. You've worked on migraines, but many people may not understand exactly what a migraine is. So could you first of all tell us, Richard, what a migraine really is, medically speaking?
Sure. So a migraine is a specific headache disorder that's characterized by pain that's usually one-sided, usually throbbing, often associated with a visual display called an aura, but always associated with something other than just pain, sometimes aura, sometimes nausea, sometimes sensitivity to light or sound.
And what do we think is going on in the brain to trigger these initially visual effects and then this throbbing, pulsing headache that makes people do other things like retire into a dark room and sometimes, unfortunately, experience nausea?
Well, for migraine with aura, which was what my study was about, there's a lot of evidence that what's going on in the brain is an event called cortical spreading depression. And in cortical spreading depression, which you can also produce very easily in experimental animals, a wave of excitation followed by a wave of inhibition marches slowly forward over the surface of the brain. And as it marches, the excitation produces, if it's in visual cortex, produces spots of light and zigzag lines, and then the inhibition produces a graying out of vision, which is sometimes called a scotoma.
And then people get the pain, but why do they experience pain?
Right, so the link between the aura and pain probably has to do with the fact that there are pain-sensitive fibers in the membranes that surround the brain, referred to as the meninges, and the aura itself directly activates these pain-sensitive fibers in the brain, which are parts of a nerve called the trigeminal nerve, and that is likely how aura initiates pain in migraine.
So in your study, you were asking, can a pulse of magnetism alter the outcome of someone seeing these auras? Does it prevent them going on to get a headache?
Well, so the method we used is called transcranial magnetic stimulation, It's a method that's been around for 30 years. The idea is that if you apply a powerful magnet to the surface of the skull, the magnetic field penetrates through the skull into the brain and induces a small amount of current flow. And depending on where you do it and when you do it, that can have either diagnostic or therapeutic applications.
So how many people did you enroll in your study, and what were the outcomes?
Yeah, so here the idea was to use a magnetic pulse to induce a current during the aura of migraine, with the idea that if you induced the current flow, you would disrupt that march of electrical activity and possibly prevent or dramatically reduce pain. So we ended up randomizing about 200 people, 160 of whom ended up treating either with the real magnetic device or with a sham device that vibrated and clicked but did not deliver a magnetic field. And we found that of the people who got the real device, 40% were pain-free 2 hours later and remained pain-free at 24 and 48 hours, most of them, whereas only 20% did that well when they were treated with the sham device. And that's a result comparable to what you see with the best of available medical therapy.
Speaking of which, I've got an email here from Serafina Anderson who says, why don't normal painkillers like paracetamol or ibuprofen work when you get a migraine?
Well, sometimes they do. And, there's like every condition, there's a broad spectrum of severity. So ibuprofen and paracetamol may work if you treat the migraine very early. If you wait and wonder if you need to treat, oral medications become less effective because migraine also affects the gut and you may not absorb the medication as well. And for people who don't do well with over-the-counter medications, there's certainly a wide range of prescription drug options that are very effective. So I'm certainly not saying this is the only way to treat migraine.
But given how common it is, very large numbers of people suffer with migraines, is your method safe, to your knowledge, and therefore what's the next step? Will we be seeing magnetic stimulators on the shelves of pharmacy shops so people can go and get one if they regularly suffer migraines?
My hope is that the answer is yes. So in the UK, 18% of women, 6% of men have migraines. So it's an extraordinarily common disorder in the UK and the US and Western Europe, really around the world. The hope is that this will receive regulatory approval as a medical device and that it will become available to people who want to use it. And there is a portable device. So for most of its 30-year history, TMS was given with a large 70-pound device that cost perhaps $25,000, $30,000 US that was kept in doctors' offices and used by medical personnel. We studied a portable device that weighs about 3 pounds. It's about the size of a hairdryer. And the intention is that people will take the device home, and when they get a headache, they'll have an alternative to reaching for either an over-the-counter or prescription medication.
Let's hope so. Thank you very much. Richard Lipton, who's at Albert Einstein College of Medicine. And that research, if you want to read up a little bit more about it, is in the April edition of The Lancet Neurology. And you can also find more about it and the references for the other news stories we've talked about today on our website at thenakedscientist.com/news.
Laying the facts bare. I say. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and Diana O'Carroll. If you would like to contact us through Twitter, it's at Naked Scientists, or you can send an email to chris@thenakedscientists.com.
Now, we're looking at some of the new innovations and applications of solar power this week, and so to kick us off, here's Ben and Dave to explain how you can make your very own solar cell.
Last week's Kitchen Science saw Dave and I standing out in the freezing cold and the rain, playing with water. Luckily this week we're looking at the sun, and so we're standing by a window with the glorious sunshine streaming through. Dave, what are we doing this week?
Well, I thought we'd try and make our own solar cell.
Aren't they quite complicated things to build?
They're actually quite difficult to make from scratch, but luckily we can use something which is quite common, which all the hard work has already been done for us.
Okay, so we're cheating a bit.
Yes, fundamentally.
Okay, so what are we using? What's the base that we're building our photovoltaic cell on?
Building the photovoltaic cell from a diode. This is a very common electronic component which only elects electricity through it in one direction. If you've got some old electronics which you can take apart, you'll probably find a diode in it. You want something with a black body and a white line drawn at one end. Those are diodes.
What do we actually use them for in electronics?
They can be used for all sorts of things. Amongst other things, they can convert alternating current where electricity is flowing backwards and forwards into DC direct current where it's only flowing in one direction.
You've got a couple of them here. They're very small. I can see this being quite fiddly if we're trying to build a solar cell out of that. What do we actually need to do?
Well, the actual diode isn't the black cylinder, which you can see. It's inside there. What we want to do is basically expose that. So we want to get rid of this black cylinder. It's basically a really brittle, probably kind of plastic, and you can shatter it off with a pair of pliers.
If we're talking about shattering plastic, we probably need to be very careful.
Yes, you will need quite large forces and bits can fly around, so I'd definitely recommend wearing goggles.
Okay, so you've got a pair of pliers and you've got some goggles on and you're going to do this into a bin to try and catch any bits that may come off.
Okay, so I've got a nice big pair of pliers and the diode. I'm going to very gently crush it, starting from one end, trying to leave the metal intact.
So what we're left with looks like a sort of sandwich of white stuff. It almost looks like glue.
Probably what you can see is probably glue. There's two metal wires coming into the central bit, which will have some semiconductor in it, some silicon, and it's probably been encased in some kind of glue to keep it nice and safe.
And this is going to be the basis of our photovoltaic cell.
This is our photovoltaic cell.
Okay, well, I've got to be honest, it doesn't look anything like any photovoltaic cell I've ever seen. Prove to me that it works.
Right, well, I've got a multimeter here which will measure the voltage being produced by something. So we'll first connect this up in the dark, and it sort of varies around sort of 20 or 30 millivolts.
So it is going up and down quite a lot. Is 20 millivolts about right for a diode in the dark?
Well, if it was actually in the dark and it's connected to a multimeter, which is essentially shorting it out, it should go down to zero.
And the fact that we've broken the case off just means that we're not quite going to get that perfect zero.
Yeah, that's right.
What if we move it into the sunlight?
Even in the shadow, it's going up to about 300 millivolts. If I get it into the full sunlight.
Wow, it's actually jumped to 0.4 volts, so it even had to change scale to stop showing us millivolts and start showing us volts themselves. So we're getting just under half a volt. How much power can you actually get out of that?
Well, voltage is only half of the story with power. The thing you need to know is volts times amps. So with the multimeter, we can change the setting to measure the current it's producing.
Okay, so we've now set it to measure amps, and it's getting 9.5, 9.6, very close to 10 microamps, so 10 millionths of an amp. That's not a lot.
No, then you multiply that by about 0.3, 0.4 volts, so that's about 4 millionths of a watt.
Although we do definitely have a working solar cell, the actual power we're getting is insignificant. But how is it actually working? What's going on?
Well, at the heart of a diode are materials called semiconductors. These are things like silicon. In fact, they don't conduct at all well normally. But if you add extra electrons to them, you make an N-type semiconductor. Or you can add holes, which are essentially absence of electrons, and you make a P-type semiconductor. Now, if you take a lump of P-type semiconductor and attach it to a lump of N-type semiconductor, you get a region where they join, where all the holes are pulled in one direction away from this region, and the electrons are pulled in the opposite direction. So you get an area with nothing which can carry charge, and therefore it doesn't conduct electricity.
But what's this got to do with shining sunlight on our exposed diode?
Well, because you've got this region which pushes the electrons in one direction and the holes in another one, if you can create electrons and holes in this region, then all the electrons will go on one side and make one side negative, and all the holes will go to the other side and make that side positive. And you can create electrons and holes by hitting an atom with a photon of light. This knocks an electron off it, leaving a hole.
So when the sunlight hits the diode, it liberates electrons, or it creates these holes, and you end up with a difference in the charge on either side, and that's a potential difference, what we call a voltage.
That's right, and then that voltage can do useful work. If you connect it to a circuit, it can drive a motor, run a computer, whatever you like.
But is this how normal solar cells work?
Yep, they're exactly like this, but much, much bigger. The actual active diode in that is tiny fractions of a millimetre across in either direction. In a useful array of solar cells, it's metres across.
And because they're so big and really better designed for the job, they'll create a lot more power than the pathetic 4 microwatts that we're getting from our diode.
Yeah, in full sunlight, modern solar cells, some of the best ones, can maybe produce up to 160, 200 watts of power per square metre.
Well, Dave, theirs may be bigger and better, but yours was made out of entirely recycled bits of old electronics. I think you can be proud of that at least. That's all we have for Kitchen Science this week. We'll be back with another one next week.
Size isn't everything, of course. And there you go. You can build your very own solar cell just using an old diode. The only problem, of course, is there is a very low output. So you'd need, we conservatively think, about 400 million of them just to power a 1-bar electric fire. But the principle is reassuringly identical. We've actually put the photos and more details about how to do that at home if you want to on our website. It's at nakedscientist.com/kitchen science. Dinah.
Thanks, Chris. Now, solar cells aren't a new concept, but they are an area of massive growth. In fact, photovoltaics, as they're known, are thought to be the fastest growing energy technology. Later on in the show, we'll be hearing about ways to make solar power and architecture work together, and how you can turn solar panels into tents to provide both shelter and electricity. But great as solar sounds, it's long been held back by the relatively poor efficiency of the cells themselves, which is what researchers are trying to improve. Niraj Lal is a researcher from the Nanophotonics Group at Cambridge University's Cavendish Laboratory. Hi, Niraj.
G'day.
So, can you tell us a little bit about why current cells are poor performers?
Well, so I think the reason why you don't see solar cells on roofs everywhere you go, is because they're expensive to make. The materials that they're made out of are pretty expensive, and also because they're not as efficient as we'd want them to be. So when sunlight hits a solar cell, some of it gets reflected off the top of the solar cell, and some of it goes straight through and then out and back again without even being absorbed.
So how can we use nanotechnology to try and improve that?
So scientists all around the world are finding that when we structure material on the nanoscale, on a really small scale, it interacts with light in different ways that we haven't seen before. And one of those ways is to concentrate light in regions that we haven't been able to concentrate light before. So on the top of a metal surface, that's what's known as plasmons, and we can use these concentrated bits of light to increase absorption in a solar cell and increase efficiency.
But how does that actually work?
For certain metals, typically gold and silver, or sometimes copper and aluminium do the same thing. When you shine light on them, if you shine light with just the right colour and you have the structures just right, you can set up a resonance inside the metal, inside the charges of the metal. So if you shine light on a metal surface and you excite these charges going backwards and forwards, you can set up a concentrated bit of light along the top surface of the metal, and that's what's known as a plasmon. And that's what we're trying to do. We're trying to use those plasmons to increase the efficiency of solar cells.
And you've got an audible example of this setting up of resonance with you. Could you give us a demonstration?
Yeah, no worries. So what I've got here is a Buddhist singing bowl. Monks use it to help them meditate. And it's a brass bowl, about the same size as a cereal bowl. And what I've got here is a wooden rod. And I'm kind of rotating it against the edge of the bowl. Now if I drive it with just the right frequency, I can set up a resonant response inside the bowl. So that's a mechanical response, a mechanical resonance. But the same thing happens with light for structures about 100,000 times smaller. And that's what my PhD is about, using structures like this to increase the absorption and increase the efficiency of solar cells.
So how do you make these nanostructures then?
Yeah, it's pretty cool. What they do is they get the beans from bean bags, so polystyrene spheres, but a lot smaller, and they put them on the clean surface of a metal. They're in the solution, and they dry them. And as they dry, they're packed into a hexagonal lattice. And when they're all dry and all set, we grow gold or silver or the other metal from behind them using electrochemistry. And as we grow them and we get to about half height or a little bit higher than half height, we stop and then we dissolve away the spheres, dissolve away the bean bags, and we're left with a kind of field of little bowls everywhere. And that's what we call nanovoids, and we use their plasmonic resonance to increase or try and increase the efficiency of solar cells.
And just how much more efficient can they become with this technology?
So last week we made a batch of solar cells that showed about twice as much electricity at certain wavelengths. And so it's a preliminary result, and we're still trying to figure out exactly what's going on, but it's exciting. Yeah.
So presumably these haven't been deployed anywhere yet. No one's using them across the world.
No, not yet. I think it'll be a while before anything like this actually gets on top of a roof. But efficiencies are increasing every year, and I think if this works in 5 to 10 years, we'll see them on roofs.
Fantastic. Well, thanks, Niraj. That's Niraj Lal, and he's based in the Nanophotonics Group at Cambridge University.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with me, Chris Smith, and also with Diana O'Carroll. And this week we are looking at the science of solar power. Now, still to come, how you can design buildings with solar energy in mind, and also flexible solar cells that you can even turn into tents. That's on the way. If you'd like to get in touch with us, you can, of course, drop us an email. It's chris@thenakedscientist.com, or tweet at us at Naked Scientists. Diana.
You might think that solar cells work best when you pack in as many of them as possible, but this isn't always ideal. We sent Mira Senthilingam out to find out how cleverly designing solar cells into the structure of a building can make them multitask. So as well as offsetting some of the energy demands, they can also act as a shade to keep down aircon costs in the summer, and as a roof to keep out the rain.
This week, I'm at the Highfield campus of Southampton University in the George Thomas building, which is their student services building. The reason I'm here and what makes this building so special is that it has a photovoltaic atrium. And so this building, as well as a few other buildings here on campus, are powered or partly powered by solar cells. And so here to tell me a bit more about the design of this building and just how much electricity it produces is Patrick James from the Sustainable Energy Research Group here at Southampton. Now, Patrick, this photovoltaic atrium is quite impressive. Tell me a bit more about the design.
We had the original building, which was in the 1960s, and we needed to expand the amount of space for offices. And so we built a new building adjacent to it. Because of the tight footprint of the space, it was better to link the two buildings together. And therefore, the designers went for this approach of an atrium, a linking space open at all levels.
So you set about designing this atrium in a way that would capture some solar energy and therefore contribute to some of the power needed by the building.
Yes, that's right. I mean, the decision was made to go for the atrium with a normal glazed roof and a shading solution with internal roller blinds. And we were asking the question, could we do the same thing with a photovoltaic glazing?
And how large are each of these solar cells that are up on the roof, and how many of them are there?
Each solar cell, as we look up, is 125 by 125 millimetres square. But these are actually formed together into what we call a laminate, which is these big sections of 3 by 2 metres. And we have 63 of those with a total active area of around about 200 square metres. And so what you can see here is a roof where the cells are spaced apart to provide sufficient daylight throughout the year for the space, but also provide a shading solution for the summer months so we don't overheat this space. The primary function is a weatherproof barrier. We must stop the rain coming into the atrium space. That's number one. The cells provide daylighting and solar control, and of course we generate electricity.
And how much electricity is generated by these?
The generation from the solar cell is dependent on the amount of sunlight and the temperature of the cell. If the cell gets hotter, its output drops slightly. This array is actually highly optimised because of the fact it's south-facing, it's an ideal elevation at around about 35 degrees, and we also get some reflected light from the roof space in front of the atrium, so we get an additional albedo effect. So because they have a very good alignment and roof pitch, they generate around about 900 kilowatt hours per kilowatt peak installed per year.
And what does that translate to for people that aren't familiar with kilowatt hours?
As a residential customer at home, 1 kilowatt hour is 1 unit of electricity on your bill, and that's what you pay 12 pence for. So 900 lots of 12 pence, so around about £100 per year worth of electricity. But we have 12 kilowatts here, so it's around about £1,200 a year.
How much of the total electricity that this building requires is that?
In terms of the electrical demand of this building, and because this is offices, the majority of the demand is electrical. This generation from the array is around about 6% of this building's demand.
And so would you say that's a good offset? Is that a good amount to be produced?
Obviously, in the UK, our irradiance levels are lower than, for example, in Spain. If we just simply move this building to southern Spain, we would generate 50% more per year. This application is really showcasing the fact that if you consider the multifunctionality of elements, that's where you can get the real benefit. It's a shading solution, it's a daylighting solution, it's a weatherproof barrier, and it also generates electricity. And when you consider all these elements together, this solution makes economic sense.
Patrick James from the University of Southampton, and he was with Meera Senthilingam, and they were at the university's George Thomas building. This is The Naked Scientists, and we're talking about the science of solar.
In just a moment, a new generation of flexible solar cells that you can roll up. If you would like to contact us through Twitter, it's at Naked Scientists, or you can send an email to chris@thenakedscientists.com.
We've heard from Peter in Godmanchester, who's wondering about solar cell efficiency. We'll answer that one for you shortly. But first, to a very interesting step forward, which is that one of the problems with conventional solar panels is that they're very heavy, they're also fragile, and they're stiff. And that means it's very tricky to transport them and to install them. And that means that a flexible solar cell that you could roll up and then readily transport would be an ideal solution. And PowerFilm Solar is an American company, and they're doing just this. They're developing what we call thin film photovoltaics. And we're joined now by Dr. Frank Jeffrey and also Mike Kuhn. They're from PowerFilm Solar, and they're going to explain to us how they work. Frank, hello, welcome to The Naked Scientists.
Thank you.
Tell us first, if you would, how does your architecture, your flexible cells, actually differ from the rigid ones that we see people putting on their roofs? How do you make them bend?
The principal part of the solar cell itself is, in our cells, amorphous silicon, which has an extremely high absorption coefficient so that we can have extremely thin semiconductor material, and that will still absorb a good portion of the light. And that thin material, even though if it were thick like a crystalline wafer would break, in that the same type structure, when it's thin enough, becomes flexible and tends to bend rather than break. So that's the key part, is our basic absorber layer that absorbs the solar energy is only, say, 5,000 angstroms thick. So it's quite thin and flexible. We put it on a thin film plastic substrate that is also flexible and adds mechanical support and strength to the solar component.
So when you say it's flexible, how flexible are we talking? Could you roll this up like a newspaper, or would it not tolerate that kind of treatment?
Well, if we have the basic substrate and solar material itself, we can roll it up diameter of a pencil, and it does just fine. And actually, some applications we do roll it that small for storage. That's mostly a space-type application. But normally we put heavier encapsulant on the outside to protect against Earth's atmosphere, and that means maybe 3-inch diameter is what a commercial cell module that we sell will roll up comfortably.
That's still pretty impressive to get it down so small. If we could zoom in with a microscope and just examine the structure of your cells, what would we see if you could just paint a picture for us so people can appreciate exactly how they're configured?
Yeah, maybe an electron microscope in order to see it, but we start out with a basic film of polyimide plastic to build it all on. So that's the bottom layer that you would see, and that may be 25 to 50 micron thick plastic film. On top of that, we put a metal layer, principally aluminum, that acts as the back electrical contact, as they're able to carry the electrons off the back surface of the solar module or solar cell. Then there are 6 layers of silicon, forming actually 2 diodes. A thick diode on the bottom that absorbs the red light, and a thinner diode on the top that absorbs the blue light. By having 2 diodes, we get a higher operating voltage and lower current, which means we don't lose as much energy in resistance of the leads coming in and out. Then on top, we have a transparent oxide conductor, and it's not all that easy to make something that's both transparent and conductive, but that's the type of film we use. That allows the light to come in and also carries the current off the face of the solar cell. So that's the stack from top to bottom, and then clear plastic, generally a fluoropolymer encapsulation, both front and back, to protect it from moisture and outside weathering and that type of stuff.
Ingenious to manage to have something that absorbs both the red and the blue so that you don't waste any energy. How much energy do you extract? So if I compared your system head-to-head with one that I could buy off the shelf to put on my roof today, how would the efficiencies compare?
If you compare to the different technologies out Ours is quite a bit less per square foot. We generate about 5 watts per square foot, as opposed to crystalline silicon, which is more in the range of 15 watts per square foot. So the output is considerably less. Part of the point of our approach also is a very low-cost manufacturing, so that ultimately we can be competitive in the cost per watt generated in specific markets that require us to be lightweight and thin, such as integrated into building panels. We can be competitive with crystalline silicon on a cost basis and in an application basis.
So no such thing as a free lunch, but I guess the payback is, and Mike, let's bring you in, Mike Kuhn here. I suppose the payback must be that you've got very good portability. There must be many applications for something like this, which can be rolled up, packaged away, and taken somewhere where you need instant power on demand in the middle of nowhere.
That's right. On one end of the continuum, we have products which serve the portable power market especially well because of the lightweight nature of our material. And on the other end of the continuum, and I'll talk more about our building integrated products, our larger scale products, which can be up to 30 feet or approximately 10 meters long for larger scale building integrated applications. But on the portable area, the lightweight is especially important because we can provide power, unlike others, that can be extremely lightweight, can be ported in, and can be extremely durable. For example, the U.S. military has shot holes through it, and it continues to perform, and that's because of this printed interconnect, which Frank developed early on for the company.
Tremendous. So in other words, you've got something which is quite literally bomb-proof. How are you actually seeking to use this? Who are your markets? Who is taking this product and deploying it in the field?
Yes, there are currently 3 primary market segments that we're serving and a 4th one which we're launching in the process of gearing up for. The existing markets that we're selling into are the commercial industrial markets, a variety of applications ranging from providing panels for GPS asset tracking on semi-tractor trailers to remote data collection, electric golf carts, campers, RV panels, the whole gamut. Also, the military market is very important for us. We've developed products which range on one hand from small AA chargers to 5 to 60-watt portable chargers to charge everything from ruggedized laptops and notebooks to medical refrigeration to remote sensors, as well as in our larger 1 to 3 kilowatt power shade products, which provide not only remote portable power, but also the shade benefit that was mentioned earlier. These are very rugged, durable products, can go over existing shelter structures, and about 4 or 5 man-hours can be set up with 2 to 4 soldiers.
So I guess that if you've got, say, a military camp, they're in the middle of nowhere, previously power had to come from someone carting either very heavy batteries or a big diesel generator and all the fuel for it. Now you've got a system where you could deploy this. It looks, because it's flexible, like a tent to all intents and purposes, and it's going to provide mobile power.
That's right. It's very much designed to meet the power needs of today's war theater, which remote outposts are incredibly important, increasingly important. Such as in Afghanistan, and we provide energy solutions which can be integrated either independently for targeted uses of power, as well as integrated in part of overall hybrid systems. One of the important aspects of our technology is it does reduce fuel consumption, which can be incredibly costly in those remote areas. Reducing fuel consumption reduces convoys, which reduces the cost of the fuel, as well as the potential risk of casualty losses with those fuel convoys.
Terrific. Well, thank you very much for joining us to tell us about your work. That's Mike Kuhn and Frank Jeffrey. They're both from PowerFilm Solar, with flexible photovoltaic cells that you can even turn into tents, and that gives you mobile power on the move. Thank you, guys. Now, Niraj Lal is here from the Cavendish Laboratory in Cambridge. Got a question for you from Peter in Godmanchester. He says, if solar cells are inefficient, how do they compare to the direct conversion of energy you would get, for instance, from a heat engine, in other words, just an engine, or simple heat absorption? Sure.
So a typical diesel generator would be about 40% efficient. And so what that means is heat energy to electrical energy is about 40% efficient, or maybe 45 for a really good one. Just recently, they cracked 40% efficiency with solar cells, solar photovoltaic cells. So the efficiencies are about the same, but for converting heat energy, your diesel engine generator or heating up a hot bucket of steam is more efficient.
When you say 40%. What sort of light are they absorbing? Are they just taking the light we can see? Or does that mean that when you measure light, obviously light's a huge, great continuum. There's light we can't see, ultraviolet and infrared, and then the stuff we can. So what's included in that calculation then?
For a solar cell, what they have is a solar cell has a band gap, so it has a particular wavelength, and it'll absorb light of all energy higher than that particular wavelength. So, definitely we can't see some of the light from the sun. Some of it's in the infrared and in the UV. But a solar cell will absorb at a particular wavelength and absorb everything that we see, plus all the UV ahead of it, and plus all the X-rays and gamma rays.
So could you make one then that will work in the dark because it will just use heat? Because that's infrared, it's a form of light, we just can't see it.
I think technically yes, but the efficiencies that you get would be really fine.
Probably not worth doing. Thank you, Niraj. This is The Naked Scientist. We're talking about the science of solar. If you have any questions for us, it's chris@thenakedscientist.com.
Distilling the best science. The Naked Scientists.
It is The Naked Scientists, Chris Smith and Diana O'Carroll. We're talking about the science of solar energy and solar cells. Quite a fertile discussion going on in Second Life. If you want to listen to The Naked Scientists live with other people from around the world, we're in Second Life and we're watching what you're saying, guys. They're all talking about the advantages of selling power back to the national grid. Now, in the country you come from, this is quite a big business, isn't it? Because you actually, in Australia, get paid decent rates for the power you generate, but here it's much more hit and miss, isn't it?
Yep. I think the economics of it comes down to which country you're in. And I think Germany, a while ago...
Germany, I've heard, you get very good deals.
They had a feed-in tariff, so that means for every bit of energy that you make that you're not using, you can sell back to the grid at a really high price, a lot higher than what you buy it back at. So in Germany and in certain places in Australia, it becomes cost-effective to have solar cells on your roof.
I still think, though, because Dr. Carl, who is a friend of ours, big broadcasting science presence in Australia, he installed a big array on his roof, and he said his payback period was still 250 years. Because they're so expensive to install. So this is the big problem, isn't it? Are the crystals and the structures you're talking about, Nidge, are they actually going to be cost-effective for people, or are we talking about something which is going to be years of development yet before we see these in place on a roof?
Yep. I'm not sure what exactly Dr. Carr was referring to, but I think if you just buy one off the shelf and put it on your roof in Australia, the payback time is maybe 10 to 15 years. But with government subsidies and government programs, and you can reduce that to about 8 to 4 years when it starts to become not a bad investment for a household.
Do the numbers stack up, though? If you add up the benefit you can get, in other words, if you take into account the carbon equation, the manufacturing cost, the transport cost, the installation cost, the running and maintenance cost, does it still benefit the planet?
Yeah.
And after how many years?
It's a good question. So a lot of solar cells are made from silicon, and that's a pretty energy-intensive thing to make. I think for a standard silicon solar cell panel, it's about 4 years that it takes of making energy in a really nice sunny place to just pay back all the energy that it took to make the solar panel in the first place. But after 4 years, it starts giving you back in carbon terms. And the life of a silicon solar panel is about 25 years plus more. And so I think it does start to make sense in certain areas in the world with government help to start off with as well.
I did some back-of-the-envelope calculations a little while back, and if you cover the whole of the Sahara Desert in solar cells, you've got the world's energy needs several times over.
Yeah, well, they're starting to...
Why doesn't someone do that?
Yeah, well, they're starting to... It is expensive to make. They're starting to think about putting solar farms in really sunny places and shipping the energy across between Africa and England. I think it's definitely one of the things to think about in concert with wind farms and wind turbines.
It's just changing mindset, isn't it? Because in Australia, the one thing I noticed a stark absence of were very many of these solar cells. Just loads of sun, not many people using them.
It was amazing. I got to go to Germany for the first time, and you just drive around and you see solar cells on the roof. You think, wow, if they can do this in a country like Germany, surely they could do something like that in Australia. But I think it's happening. I think people are thinking about it more and talking about it more, which is a start.
Got to start somewhere. Niraj Lal, thank you very much. Now, from spending money on electricity, Diana, to, well, making it.
I wish. This week it's all about how we can make a mint of our own.
Hi, it's Dominic from Newmarket. I'm just calling about how money is made and how the different colours are formed.
So let's start with the notes first. How do they survive the wash?
My name is Mark Cricket and I work for the banknote printers De La Rue. Okay, essentially it starts, not surprisingly, with the paper itself, which is manufactured from cotton rather than wood, which is used for most of the papers that are used in other applications. The reason that cotton is used is to make the notes more durable against the rigours that they'll face in circulation with the public. And it also, when it's combined with the printing processes, helps to give the banknotes the unique feel, which makes them feel different from other printed documents. The process that we use is a very old process, quite an unusual process that's not used now for commercial paper production, and that enables us really to put in the distinctive tonal watermarks and the metallic strip, which we call a security thread, which runs through the paper and is inserted when the paper is manufactured. What we then do is we take the paper and it runs through really a number of printing processes. The first process, which is known as litho, puts on really most of the colours and provides most of the back of a Bank of England notes and much of the front. The second process, which is a very unique process used in banknote printing, which is called intaglio, which actually uses an engraved plate, and ink basically goes into the engraved, it's like grooves in the plate, and is then forced out under pressure, and that helps to produce a very distinct tactile feel to the notes, which again is an important security feature for the public to recognise. Some of the elements, for example, that are printed by this process is the portrait of Her Majesty the Queen. And then really the third main process is known as letterpress, and that's used to put the unique serial number on each note, which obviously is used to help keep track of the notes.
But what about the coins?
My name's Matt Bonacorsi, and I'm Chief Engraver at the Royal Mint in South Wales. Okay, well, we obviously start off like any other product with a design. Once that design's completed, we then have to turn it into a 3D or what we call 2.5D object, which is the sort of sculpted version that you're going to see on the coin itself. These days we use a lot of computer CAD sculpting, and if you can imagine, it's a three-dimensional map of the coin on a screen that is 4,000 by 4,000 pixels. So that gives us 16 million points of information within that screen, and each one of those points is a coordinate, and we feed those coordinates into our CNC engraving machine, which is basically like a tiny revolving cutter that will then move over a blank piece of steel following those coordinates, and as it works its way around, it gradually builds up a picture of what the finished coin looks like. But obviously when we stamp a coin, the stamps that actually impart the design onto the surface of the blank, those stamps, which are called dies, have to be back to front. So we take our steel piece of tooling with our coin design on it, and we press it, we put it under a hydraulic press and squeeze it into a soft piece of steel so we can take a negative impression from that. And it's that negative impression that's then put on a lathe and turned to the right shape and size to fit into one of our presses, and that's what will actually stamp the coin itself. Forgery is obviously a key part of what we do. The metal composition of coins is key to that. The percentages of different alloys that go into coins are very, very closely monitored and very, very closely controlled. So it becomes very difficult to replicate a coin that will read in vending machines or that will look or feel the same as a real coin.
So notes are made from cotton and some very secret inks, some of which are magnetic, others can only be seen in UV light, and some are only visible when they become warm. Coins can also be protected from forgery using clever design tricks, such as a latent feature in the £2 coin, which is a design that changes as you move it in the light. But their main form of defence is in using very specific metal alloys, which are also kept secret, of course. An interesting fact of the day, I didn't know this before, but the Royal Mint actually supplies over 60 countries with their coins.
That's amazing. When they press out a coin, do they call that quantitative squeezing?
Oh.
Sorry, I didn't know that. How much do they charge to actually do that?
Yeah,
then?
Maybe it changes with the exchange rate. I don't know. But now from coin bending to mind bending for next week's question.
My name is Julie Lani Chang, and I live in Davis, California, and I have a question. My question is there any science to the companies that sells or claim that their subliminal CDs could actually alter your behavior simply by tapping into your unconscious mind?
Do you know how subliminal learning works? If so, then brainwash us all with your answer. Email unconsciously to chris@thenakedscientist.com or write about how you want to give all your money to me at thenakedscientist.com/forum.
Thank you, Diana. And you can catch Question of the Week as a podcast in its own right. Find it on iTunes or on our website. That's at nakedscientist.com/QOTW. That's it for this week. Thank you very much to our guests who took part: Richard Lipton, Niraj Lal, Frank Jeffrey and Mike Kuhn, and also to our production team, Ben Valsler, Mira Senthilingam and Dave Ansell. Join us next week, on the other hand, for our Naked Scientist Science Phone-In extravaganza. We'll be answering all of your science questions and bringing you an update from the Cambridge Science Festival. So, if you want to know how many organs you can donate and still remain alive, how many heartbeats you can count on in the average lifespan, or why a dog's eyes glow demonically when you shine a torch at your dog in the dark, send your questions in. It's chris@thenakedscientist.com. Thanks for listening, and until next time, goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.